Hi, this is the oral presentation to our Pac-Man design. We are Team 256. First, we will talk about the design for our final AI solution. We have used multiple techniques. The first one is heuristic search, and the second one is Monte Carlo tree search. We also try approximate Q-learning and TD, but we find out that the performance is not that well, and we will discuss about this in the later part. Our AI solution contains one offensive agent and one defensive agent. First, we will talk about technique, heuristic search. Heuristic search is the core technique for our solution. It is a technique that uses heuristic function to generate information, and we use it as the feature and we calculate ranking for each actions. In our model, we use weight feature models and we leverage multiple heuristic functions to generate output as feature and calculate overall ranking for each actions. In this part, we'll talk about the Monte Carlo tree search. We'll leverage the simulation part of Monte Carlo tree, and it allows us to simulate the future game state after taking a series of action under a certain policy. This is our solution to the food in block area situation. When our Pac-Man's nearest food is inside a block area that has only one entry, we use simulation to see how many steps it would take for our Pac-Man to enter the block area, eat a certain amount of food, and leave. Then the Pac-Man can decide how many food it would eat in the block area without being blocked or eaten by ghosts. We simulated maximum 20 steps since the block area that takes more than 20 steps to work around is dangerous enough for the Pac-Man to decide not to enter.
We have encountered several challenges during the implementation of this project. The first is that the provided function getMazeDistance only returns the length of the shortest path from the first position to the second, ignoring all other paths. However, in order to avoid enemies, our Pac-Man needs to take longer paths to get to its target sometimes. So we designed a go-around function to solve this problem by conducting a breadth-first search from the current position to find a middle point whose shortest path to the target is clear of ghosts. Also, our defensive agent sometimes wastes time going after the opponent's defensive agent that never eats food. So we try to keep a record of indexes of the opponent's agents who has ever carried food. So our defensive agent won't waste time anymore. There are several further improvements I think we can do if we have more time. First, a defensive agent can perform better if it could predict the intention of the invading Pac-Man. Second, eating capsules and opponents more wisely to maximize the time the opponent's being scared. Third, an offensive agent's path can be planned better to eat as many as food per step instead of always going for the nearest food first. Fourth, after eating an opponent, its distance can be estimated using the knowledge of the opponent's start point.
And we also tried approximate Q-learning. So we're also thinking about maybe adding time into our features, because when we're doing Q-learning, our Pac-Man doesn't really know that they have to go back because the time's almost up. And the next point is when we're using approximate Q-learning to shape weights, we tried it, but the weights are actually a bit hard to control and they're sensitive to changes in features. For example, food left on the grid is actually very intuitive, but when we implemented it, it doesn't work very well. And the next point is we're thinking about maybe we can apply game theory to let our agent to auto switch between offender and defender. And this is our demo for the approximate Q-learning technique we tried. And this one is that it used to stuck in the corner until the end of the game because there's not much reward in the neighborhood. But after we use approximate Q-learning to shape weights, it learns to escape from the corner. So here's the demo. At first, it's stuck at the corner, but after some time, it goes out and to school. And the second demo is also using approximate Q-learning. We observe this behavior that it learns to go around the ghost instead of just going to the opposite direction after we use weight shaping. So here's the demo. Like, it doesn't just go away from it, but it actually like go around, and sometimes it traps the ghost into following it, and then the Pac-Man can escape.
Sometimes there are food in blocked area. Our offensive agent will decide whether or not to eat those food depending on how many steps it will take to eat those food and the distance of ghost. We can see in this demonstration that at the same position, the Pac-Man makes different decisions. This is the demo of our bypassing ghost functionality. When the shortest path of our agent to home is blocked by a ghost, the agent will conduct a breadth-first search to find a neighboring position that has a clear shortest path to our target. So we can go around the ghost and get to the target. In this demonstration, we can see that once our defensive agent has blocked an enemy's Pac-Man, it will stop. So the enemy will be checked until the end of the game.